years now, and today I'm going to talk about blockchain, the distributed web. So, to give it a little history, do people here know what Bitcoin is? Raise your hands. Yeah? Good. Okay. So, for those of you who don't know, Bitcoin is the first practical application of a decentralized currency. It was created in 2009 by Satoshi Nakamoto, and he published a paper called Peer-to-Peer Electronic Cash System. He built upon some cryptographic concepts and like public key cryptography, and he combined it with a consensus algorithm known as proof of work. With this, he created the Bitcoin network. In the Bitcoin network, there is no one source of truth. All the nodes in the network share the truth, and any node in the network can participate in the consensus mechanism. It's important to note that when Satoshi created the first transaction for the blockchain, he included the message, "Chancellor on the brink of second bailout for banks." This is interesting because it gives a sense of the motive of why Satoshi created blockchain and Bitcoin. It was a direct critique to the fractional reserve banking system in the context of the 2008 financial crisis. Okay, so to build a blockchain, we need to understand a few key concepts. The first is a hash function, or hash. A hash function maps data of arbitrary size to data of fixed size. We have a couple of examples here. The first example is the string "Welcome to Fullstack Nights." It's 27 bytes long. Even though it's 27 bytes long, when you pass it through the hashing function, it renders a hash or output of a fixed size. So if we were to hash an image of 45 kilobytes, we would still get a hash of the same size as the hash of the short string that doesn't have that many bytes. With hashes, we can build a Merkle tree. A Merkle tree is a data structure that allows for efficient and secure verification of the contents of large data structures. So I borrowed an example that uses some color theory to explain how a Merkle tree works. So for those of you who know a little bit about color theory, when you mix colors, you get another color. So if we look at, on the left-hand side, we look at the first row, we have the yellow and red, which create orange, and the green and blue, which create kind of an aqua color. And then when you mix the orange and the blue, you get like a teal green color, right? So let's say we were to change just one block in the top of the tree. So we were to change the green block from green to purple. Then the mix of the blue and the purple would render another color that's different from the original aqua. And then the orange and the purple would mix again to form another color, which is the plum color here, that's different from the green color. So basically, this is a simplified example of the Bitcoin blockchain. It uses a Merkle tree, which contains a block of transactions are generated approximately every 10 minutes. When the transactions are pulled together, they get hashed, as in the first concept, and you get a hash. And then it gets put into the blockchain, and it has a new Merkle root. So whenever new transactions come in, they have to reference the Merkle root of the past of the other transactions that have been hashed. This is a really simplified example, and it's a very interesting concept, and it's a very deep concept. And I suggest that you guys take some time off to if you're interested, to research more about this, as it falls outside the scope of this presentation. Okay, so with that said, we can jump into the kind of the main part of the talk, which is the focus of the talk is how you build distributed applications. I just have to give you a little history of the data structures that take to build blockchains. So in a distributed application, there is no client-server model. Traditional legacy systems, they had a client and a server, and all the clients have to connect to that same server to have the source of truth. In a distributed application, every node in the network has the source of truth. It's shared amongst all the nodes. So we're going to talk about the concept of distributed application, which is called a dApp. Okay, so this is really interesting. A apart from Bitcoin, there exists another blockchain that was created some years ago that's called Ethereum. In the Ethereum's website, you can just see built unstoppable applications. Ethereum is a decentralized platform that runs smart contracts, applications that run exactly as programmed without any possibility of downtime, censorship, fraud, or third-party interference. That's a bold claim. So, the Ethereum system has some basic components. It has the Ethereum virtual machine, which is a compute part of the equation. It has Swarm, which is decentralized storage, and it has Whisper, which is decentralized messaging. But those I leave that up to you to research that. I'm going to talk about the main part, which is smart contracts, and which is the paradigm shift here. Smart contracts are basically classes. You can, like a class in C, or like a class in Java, or whatever. They are basically state machines. So a smart contract lives inside a sandbox, which you can store data in. So a smart contract has private variables, public variables, methods, events, and storage. So you can store whatever data you want inside the smart contract. There are two types of accounts in the Ethereum network. You have normal accounts and you have contract accounts. Normal accounts is any account that's not a contract. Normal accounts can communicate or transact with other normal accounts. So let's say I can have an account and you can have an account, and I can send money, Ether, which is the cryptocurrency in Ethereum, to you. As well as contracts can send Ether to other normal accounts or other contracts, so they can interact between them. To build smart contracts, there's a few programming languages. The first one is Solidity. Solidity is a programming language like JavaScript syntax. Serpent is a programming language like Python syntax. And LLL is a programming language like Lisp syntax. Okay. Another interesting project is called IPFS. IPFS is the Interplanetary File System. It's a distributed file system that stores content, and the content is addressed by the hash of the content. So let's say you upload a file, you get a hash of that file. Then if you want to get that file from the network, you just call the network with that hash and you'll get the file back. It basically combines Kademlia, BitTorrent, and Git. And Kademlia is a distributed hash table. And it works, I mention it here because I've been using it in some projects, and it works really great with Ethereum. As I mentioned, in an Ethereum contract, you can store data. But the thing is that the more data you store, the higher the network charges you for storing that data. So we want to store as less data as possible in a smart contract. So let's say we would upload a file to IPFS, we will get the hash, and then we would save that hash in the smart contract. Then we can reference the contract, get the hash, and do whatever we want to do with the file. So this is a kind of a crude example of a dApp structure, dApp architecture. You basically have to think that an Ethereum node and an IPFS node have to run in your machine. Let's think about the context of a development machine. You're developing an application, and you have in your local network running an Ethereum node and an IPFS node. Then you would create some JavaScript that lives in your local machine, and you would instantiate a Web3 client and an IPFS client. So you would interact, the front-end JavaScript interacts with the IPFS client and with the web client and the Web3 client, and then they interact with the respective nodes. The client never communicates with the network. Only the nodes communicate with the network. To start the development process, you use a private blockchain that lives in your machine that's called TestRPC. So you can start building a smart contract or a distributed application in your local machine without having to upload the contract to the testnet or the livenet. When you upload a contract to the testnet or the livenet, that contract is permanent. And that's a kind of paradigm shift that it took me a while just to get around it and think about how you work with that. Since when you deploy a contract, it's permanent. You can't change it. The code is as is, and it's guaranteed to execute exactly as it's programmed, and anybody can see the code in the smart contract. whenever you're ready, after you use test RTC, you unit test your contract, you make sure it works, then the best practice is to go through a bug, a bounty, and an audit, so you can make sure that your smart contract doesn't have any bugs. There have been issues with some smart contracts that have been zero-day exploited because they didn't check all the possibilities of the contract, and then an attacker can take advantage of that. There is a way in which you can have versioning of your smart contracts. You basically would have one main contract that acts like a router. So whenever you deploy a contract, you get an address. And then you can have one contract that references another version of your contract. So, okay, so this is an example of a smart contract written in Solidity. So you can see the contract, it's called FSN dApp. It's basically a name registry, simple name registry, that anybody can claim a domain name and point it to an IP address. The first few lines are just variables for the contract. Solidity is it's a strictly typed language, and I would recommend that if you want to dabble with it, you learn about all the types and how to use them. As you can see, like in line number 6, we have mappings. Mappings are like associative arrays. So you don't have arrays right now in the Solidity language. You have mappings. So whenever you want to store key values, you use a mapping. It's important to note that the constructor always has to have the same name as the contract. If not, you'll have problems. And so let's go now to a method. So we have the register domain method, which takes as arguments the domain name and the IP. So we first check if the domain exists, if it's already been added to the mapping. If it does exist, then we just throw. If it doesn't exist, then we can increment our internal counter by 1, assign the new domain its IP address, and add the sender to the registry and map it to the domain. We want to do this because just the person who registered the domain is the only one who can then update it. I, as the creator of the contract, I couldn't update it because it right there says in the code that only the message sender can update the domain. So, can register the domain. So in the other method of update domain, it's basically what I just explained. If you send a transaction as the owner of that domain, then it's no problem. You can update the IP address if you change it. So another method is the get destination method. It just you pass the domain and it returns the IP address. So basically like a name registry. Okay. To deploy these, there are a couple of steps. You have to start an Ethereum node in your local machine. You have to compile your Solidity contract and get back its binary. After that, to deploy a contract, you have to send a transaction to the network without a recipient. But in that transaction, you have to include the bytecode of the compiled contract. You get back what's called an ABI, which is a JSONified representation of your compiled contract's variables, events, methods that you can call. After you have all this, you can then call your contract's methods and interact with it. Okay, so this is a Node.js script on how to interact with your smart contract. So you already have your ABI, so you would have to read that from, it's a JSON file, you read it from disk. Then you instantiate a new Web3 client, and then you pass the ABI to the contract, and then you instantiate the contract with the address you got provided when you first deploy the contract to the network. So with all that, then you have an instance of your contract. Now that you have an instance, you can interact with your contract. There's also a couple of ways, there's a few ways you can interact with your contract. You can have events. Let me go back. So if you see here, the registered domain, it was declared at the top, it's an event, right? And you can declare events and call them when a method is called. So let's say somebody registered a domain. So perfect. Since somebody registered a domain, the registered domain event gets invoked. Then since you're watching it, you get it in your, you get it there. You can know what you can know the registered domain event got hit, and then you can do whatever stuff you want to do with the data that comes from it. The other two important ways is on how to interact with a contract are you can send a transaction or call a function. It's important to note that when you send a transaction, you are changing the state of the contract. So let's say if we want to add a domain, that would be a transaction that changes the state of the contract. So that costs gas, that costs money. So whenever you want to create something or change the state of the contract, you have to send money to it so that the network gets paid for processing your code. The other way to do it is you can call a function. You basically ask for a variable. You don't change state. You just call a variable and you get it back. That's for free. But whenever you need to change state, you have to send a transaction. Here these are attributes that are you have different accounts. I send it from my main account and I added the base gas cost for that operation. Okay, so the Ethereum ecosystem is getting started, has been going for a few years, but there are very interesting projects coming from like decentralized energy markets, prediction markets, IoT and the sharing economy. There's actually this great project called Slockit, which is a company that makes locks that you pay the lock to, let's say, unlock your door. So you're actually paying the lock. The money goes to the lock. It doesn't go to a cloud or something. It goes actually to the lock, and then it unlocks, and somebody can use your house or whatever. It's easy to do P2P lending, decentralized crowdfunding. There's a concept, very interesting concept called the decentralized autonomous organization, in which is this entity that lives in the blockchain that people can interact with it, and it handles funds. So let's say we have a group together and we have governance for that group, and we have to decide between all of us how we're going to spend the funds. So the decentralized autonomous organization has some funds, and then we make proposals to the organization, and all the members vote on those proposals, and if that proposal passes, then the DAO releases the funds to whatever project there is. So yeah, that's my talk.